Up to this point, usually we define the state as something that we already have, like the inventory we have at the beginning of the year, the amount of cash that we have at the beginning of the month, and so on. Now, in this example, it shows us that it's also possible that we have the states saying that that is the amount that we still need to do to build or something to reach the target. So instead of what we have got so far, the states can also be what we still need to do or to achieve. In this example, Sunco Oil needs to build refinery capacity to refine 5,000 barrels of oil per day and 10,000 barrels of gasoline per day. And there are 4 possible locations to build the refinery capacity. The cost of building a refinery at site T that has the capacity to refine X barrels of oil and Y barrel of gasoline per day is CTXY. So the cost depends on the site T, and it also depends on how many capacity for oil X and how many capacity for barrels Y. How many capacity for gasoline, sorry, Y. And then what we would like to do is decide how much capacity should be located at each site to minimize the cost, I think. You may pause the video if you would like to read the problem carefully before you continue. Now the stage here is the site T 1, 2, 3, 4. And the decision is quite clear. How much capacity, how much refinery capacity to build at site T for oil, XT, and for gasoline, YT. And then the states such that you can make a reasonable decision is that you need to know how much you still have to build, both for oil, let's say OT, and for gasoline, GT. The reason here to define the states is that because we have a specific target in which we need to build 5,000 barrels of oil per day and 10,000 barrels of gasoline per day. So these are the targets that we need to meet. Suppose you already built all those 5,000 and 10,000 in the first site. Of course, your decision is on the second, third, and fourth site, you just build nothing, right? Because you have achieved the target. So that's why here we define the states as the capacity that we still have to build, both for oil, OT, and we still have to build for gasoline, GT. Again, because we have a specific target that we need to achieve, and actually once we have achieved that target, then we don't need to build anything else. Of course, there might be another way to define the states and decision, and there's the states and they're still correct. Probably there is another way, but this example shows us that defining the states this way is kind of the most logical. Okay. So here's the recursion for the very last stage. So that is the minimum cost from site 4 until the end of the problem. If at the beginning of site 4 we still have to build O4 barrels of capacity for oil and G4 barrels of refinery capacity for gasoline. And then obviously whatever we still have to build, we have to build it because this is the very last site that we can build the refinery capacity. So whatever we still have to build, we must build it such that the cost becomes C4, O4, G4. Of course, there's a possibility that O4 is already 0 and G4 is already 0, such that it's okay. We will have C4 0, 0. That is allowable, but remember at this point, because we're working backward, we don't know yet what is the value of O4 that and G4 that is optimal. So we just write down the formula that whatever we still have to build, we have to build it at the month 4, at the site 4, I mean. Now for the stage, before the stage 4, we can have the decision to build xt and yt, in which xt may not be equal to ot and yt may not be equal to gt. In particular, xt is between 0 and ot, including 0, including ot. Means that maybe you don't want to build anything. Maybe you want to build all the remaining target that you still need to build. Same for gasoline. Maybe you still have GT of capacity that you still have to build, but you decide to build nothing. That is okay. Or you build all the required remaining capacity for gasoline. That is also possible. Okay, so these are the allowable decisions for XT and GT. So that is the minimum cost from year T until the end of the problem. If at the beginning of year T we still have to build the refinery capacity of OT for oil and GT for gasoline. Well, actually this should be site. I'm sorry, not year, but site. But you know, you got the idea, right? Okay. So this is the cost of building the refinery capacity for XT and YT. Remember that XT and YT may not be the same as OT and GT because this is not the last stage yet. Okay, so here the decision is XT and YT, and you notice from the previous slide, if it is the last site, then the decision is OT and GT. So if you build XT, it means at the next stage, T plus 1, your obligation is reduced from OT to become OT minus XT. Similarly for GT, at the beginning of site T, your obligation is to build GT. Now after this site, your obligation is reduced to become GT minus YT because you already built XT and YT at this site. Okay, now here you have the small x I y I. It means among all possible, sorry, this should be xtyt. So you have xtyt here. It means that among all possible values of xt and yt, between building 0 and building everything that we still have to build, we would like to find the one that gives us the minimum cost. So in this case, what are the 3 aspects? Well, this is the first aspect because it shows us the allowable decisions, how much you built at site T for oil and how much you built for site T for gasoline. So this is aspect 1. And this is aspect 2, the cost of building XTYT at site T. And then that is aspect 3 because it shows what happens at the time T plus 1, at the site T plus 1, I mean. So those are the 3 aspects from the problem. And then remember what is special about this problem. It says that the states here are the amount that we still have to build. Okay, so this example shows that the state can also be something that we still need to do. It doesn't always have to be something that we already did or already have. Okay, so that's the end of this video, and see you on the next one. Thank you.